In this video here, we're going to take a look at successive oblique impacts. Now we can solve problems involving successive oblique impacts of a sphere with smooth plane surfaces. And when we're solving problems involving successive oblique impacts, it's important to consider each impact separately, as well as drawing separate diagrams for each one. And I'm hoping here that it should go without saying, but just make sure then that you've watched and are confident with the material from the previous video on oblique impacts with a fixed surface. So to finish with here, then let's just work through a practice question together to build on these ideas. So let's just get started then with this practice question here. Now what do we have then for this question here? Well, what we're told then is two vertical walls meet at right angles and a smooth sphere slides across a smooth horizontal floor, bouncing off each wall in turn. Now, just before the first impact, the sphere is moving with this speed here, so 2 meters per second at an angle of 30 degrees to the wall, and the coefficient of restitution between the sphere and both walls is 1/4. So, for this question here, we want to find the following two things here. So, let's just get started then with part A here. So, for part A then, what we want to find here is the direction of motion and speed of the sphere after the first collision, and as it says here then, give the speed to three significant figures. Right, so as we mentioned in the introduction here, we need two separate diagrams, right? So for the first diagram here, this will be after the first collision, okay? So I'll draw my diagram, I'll draw it here, right? So this is for the first collision. Just make a note here. So first collision. So as the question tells us, then we have two vertical walls that meet at right angles. So if I draw this here, we'll get something like this, right? They meet here at a right angle. Okay. So what I've got here then is our smooth sphere. I'll just draw it like this here, something like that, right? It then travels towards the wall here. Okay. So it slides across a smooth horizontal floor. And it bounces off this wall here, like so, okay? And it bounces off like that, okay? So we'll get something that looks like this. The initial speed here, so just before the first impact, the sphere is moving with this speed here, so 2 meters per second. I'll just call this the initial speed here. So 2 meters per second, like so. The angle here then, so it's traveling with speed 2 meters per second at an angle of 30 degrees to the wall. So that angle is this angle here. I'll try and just draw that in a different color, just so it's a little bit clearer here. So that's this angle here, which is 30 degrees. As you can see, my diagram probably should have been a little bit bigger, but I'll try and make it through anyway. So this angle here is 30 degrees, as we're told in the question. This angle here, we don't know what that is, right? We want to find what that is, because that will give us the direction of motion. So I'll just call this angle here theta. Okay, we don't know what that is, but we're going to find that a little bit later on. And what I also need here is this, V1. Okay, so where do we begin here? Let me just go back to my original pen color then. We can just note here that the component of the ball's velocity parallel to the wall is unchanged, right? So what that means here then, so to make a quick note here, the component of the ball's velocity this is parallel to the wall, is unchanged. Okay. So as we just said then, what does that mean here? Well, in that case then, what we get here is V1 times cos of this angle here. So V1 cos theta is equal to then this speed here, which is 2 times cos of this angle here, right? That's 2 cos 30. So 2 cos of 30 degrees there. So we can simplify this here, right? Because we know then that cos of 30 degrees here, the exact value of that is √3/2. So what I've got here then is V1 cos theta is equal to 2 times root 3 over 2. The 2's just cancel, and we just simply get root 3, right? So we get root 3 there, like so. What we can also do here is just use Newton's law of restitution for motion perpendicular to the wall here. Okay, let me just make another note here. So using Newton's law of restitution, I'll just abbreviate this here to LOR, law of restitution, for motion perpendicular to the wall. So perp to the wall here. What does that give us then? Well, what we get here, what does this tell us? So what we get here is I get V1 times sine of this angle here. So V1 times sine of theta is equal to, so what I get here is the coefficient of restitution here, which, as we can see then, is, I've given it as 1 over 4, but this should be 1 over 2 here, sorry. So this should be 1 over 2. I'll amend that on the actual worksheet. So the coefficient of restitution here between the sphere and both walls is 1 over 2. So apologies there. 0.5 of 1 over 2 is what we should get. So what I get here then is E, which is my coefficient of restitution, right, which is 1 over 2. And then times this by this speed here times by sine of this angle here. So I've got a half times 2 sine 30 degrees. Perfect. There we go. I was looking at my notes here and I was going to say something is definitely wrong. But yes, this here, the coefficient of restitution should be a half. So again, apologies for that. I will amend that on the worksheet. And again, I can just simplify this here, right? So a half times 2 sine 30. Once we simplify that here, I can't even speak now. So V1 sine theta is simply a half there. Okay, perfect. There we go. And what we can now do here is eliminate V1 and find tan theta, right? So let me just make a note here. So now eliminate. So now eliminate V1 and find tan theta. Okay, perfect. So let's just do that then. So to eliminate V1 and find tan theta, we just take V1 sine theta and divide that by V1 cos theta, right? The V1s will just cancel, and you should be aware then that sine theta over cos theta is just simply tan theta, right? It's one of our basic A-level maths trig identities here. So as I've just said then, V1 sine theta all over V1 cos theta. That is, well, V1 sine theta is a half, so I get 1 over 2 all over then V1 cos theta, which is root 3. So this here, the V1s just cancel, sine theta over cos theta is tan theta. So therefore then, tan theta here is equal to, so 1 over 2 divided by root 3, that's just the same then as 1 all over 2 root 3, right? So 1 all over 2 root 3. Perfect. Okay. And we're nearly there now, right? So if I just want theta here, I just take tan inverse of both sides, or arctan, whichever you prefer. Either's fine. Completely up to you. But therefore then, so therefore here, theta is equal to tan inverse of this here. So tan inverse of 1 all over 2 root 3, like so. Just put this into your calculator here. And if you do this correctly then, 2, 3, significant figures here, I get 16.1 degrees. Okay, so 16.1 degrees there. That is 2, 3 significant figures. But we're not done here because what I also need then is V1. Now we can easily just find V1 then by either just using this equation here or this equation here. It's completely up to you. I'll just use this equation here, right? So V1 then, so V1 here is equal to a half divided by sine theta. Now sine theta then, so I'm going to let theta here be this value, right? 16.1. I get 0.5 all over then sine of 16.1 degrees here. Again, just put this into your calculator. And we're giving the speed here to 3 significant figures as well. So if I do this correctly then, what I find here for V1, if I put this into my calculator correctly anyway, is I get 1.80 meters per second. Okay, so 1.80 meters per second there. Perfect. So that gives us the solution here to part A, right? What I've got here is the direction of motion and also the speed of the sphere after the first collision, right? Perfect. So this here is the solution to part A. As I can see here from the recording software, we've just hit 10 minutes alone for the first part of the question. So again, just as you can see, and just as we saw with the previous video, these questions here really do take quite a bit of time to work through. Okay, but hopefully part A there makes sense. And for part B then, well, the working is pretty much identical, right? The only difference here now is I now need to draw a second diagram. So for part B then, we'll do that over here. And what I'll do here is I'll just split this off, right? So let's just split this off over here, something like that. I've kind of gone to the right with my line here, just so I've got a little bit more room. As you can see, these questions do take quite a bit of space as well. Right, so for part B then, let's just start by drawing our second diagram here. And I'll do this for the second collision, right? So second collision. So again, we have our two vertical walls, right, which meet at right angles. So it won't look any different on that basis. Something like this here. They meet at right angles. What's different here then is the sphere here just carries on, right? It's going to carry on from, say, here to the wall, like that. It's going to hit the wall and it's going to bounce off. Okay, something like that. My diagram is not perfect, but I don't have a ton of room here. But you get what I'm trying to draw, right? So it's going to look, say, something like this here. And what do we know here then? Well, I know this angle here. So this angle here is going to be then 90 degrees minus this angle here. So just be very, very careful. This angle here is not this. It's not 16.1 degrees. It's going to be 90 minus this here. Okay. So I'll just do that in a different color here just to make it a little bit clearer again. So this angle here, that is 90 minus then 16.1. So what does that give us here then? So for this angle here, what I get then is 73.9 degrees there. What about the speed here then? Well, the speed here is just simply V1, right? So what do we obtain for V1? That was 1.80 meters per second. So the speed here is 1.80 meters per second. In fact, I'll just do it underneath then, just so I've got a little bit more room here. Let me try again. So I'll do it over here actually. So 1.80 meters per second. Perfect. And then what I want here is this angle now. So I want this angle here. I won't call it theta again. This time now I'll call it alpha. Any letter that you want to use here is fine, or any Greek letter is fine here. So I'm going to call that alpha. And I want this speed here. Apologies, I'm losing my voice. I want this speed here, right? So that is V2. Okay. So it follows pretty much in the same fashion as what we did for part A, right? So again, the component of the velocity parallel to the wall is unchanged here. Okay. So let me just get my original pen color here. So the component of the velocity, component of ball's velocity parallel to the wall. The wall is unchanged. Perfect. So again, what does that mean here? Well, what I get here then is the following. So I'm going to get V2 cos alpha. So V2 times cos of this angle here, which is alpha. V2 times cos of alpha. Obviously, if you use a different letter here for this angle, then you'll get V2 cos of whatever you've chosen here. Whatever that letter is, it really doesn't matter. But v2 cos alpha is equal to then this speed here, so 1.80. So 1.8 times cos of this angle here, right? 73.9. So 1.8 cos 73.9 degrees there. Okay. So let's just simplify this here then. What do we get? So v2 cos alpha is equal to, so if you evaluate this here, we get 0.49923 significant figures. It's a little bit painful, right, that doesn't round nicely to 0.5 here, but we'll just take it as 0.499. 0.499, that is a 0 there. So let me just avoid any confusion here. That is a 0. So 0.499 there. Perfect. Okay. Again, just as we did here, right? We're now going to use Newton's law of restitution for motion perpendicular to the wall. So again, I'll just make a note here. Using Newton's law of restitution. Using Newton's law of restitution on motion perpendicular to the wall. For motion perpendicular to the wall. Well, in that case, then what do we get here? So I'm going to get v2, so that's this speed here, v2 times sine of this angle here. So v2 sine alpha. Again, if you have a different letter for this angle, then that would be your letter here. It doesn't really matter too much, but you get what I mean, right? I'm just trying to stress the importance of that. So v2 sine alpha is equal to then. So again, I now need to use the value here for our coefficient of restitution. I'm losing the ability to speak here, but we're nearly there, right? 60 minutes and we're still going. So the coefficient of restitution here is 1 over 2. So I get 1 over 2 times by, it's tiring me out. So 1 over 2 times by, so it's going to be 1.8 times sine of this angle here. So 1.8 sine of 73.9 degrees. There we go. So let's just simplify this here. In that case, then v2 sine alpha is equal to, so again, just give this two free significant figures here. I get 0.865. So 0.865 here, like so. And again, all we now need to do here is just eliminate v2 in this case here, because we have v2, and find tan theta. So again, v2 sine alpha all over then v2 cos alpha is equal to, so I get 0.865. So 0.865 here all over then 0.499. 0.499. If we evaluate this here, then what I get is tan alpha, and then I said tan theta. So it's tan alpha in this case here because we're using alpha. So tan alpha is equal to, just put this here into your calculator. It's pretty much just going to double, right? Because I'm dividing by essentially 0.5 here. So it's basically just going to double. So what I get here then is 1.73. So if we just want alpha here, right? Therefore, then alpha is equal to tan inverse, or arctan again, whichever you prefer here, of 1.73. Put this into your calculator here. And what you get then is 60 degrees to 3 significant figures. So 60 degrees to 3 SF here. Perfect. That's beautiful, right? That we get 60 degrees here to 3 significant figures. Not some disgusting angle like, I don't know, 16.1 here. We get this nice round answer. So 60 degrees there. Perfect. And then what about the speed here? So for part B then, just be very, very careful. It says give the speed to 1 decimal place. Now, this is a little bit unusual, right? In your kind of exam question, it probably won't ask you to give the speed to 2 different degrees of accuracy here. So in part A, it's to 3 SF. In part B, it's to 1 decimal place. The only reason that I'm doing that here is because I've quickly written the question. And unfortunately, the speed here for part B didn't round nicely as I wanted it to. So I've kind of just put it here as 1 decimal place, just so it rounds nicely. If you put it into your calculator, you'll see what I mean here in just a moment. But then For V2 here, so for V2 here, again, all we need to do here is just use then either this equation here or this equation here. It really doesn't matter. Either will give you the correct answer as long as you do the preliminary working correctly. But V2 here then is equal to, so if I just take it here as 0.499 divided by cos of this angle here, so 0.499 all over cos of 60 degrees. Again, just put this into your calculator here. And to one decimal place then, what I get here is 1 meters per second. Okay. And there we go then. That is to one decimal place. Just make a quick note here. 1 dp here for one decimal place. And there we go then. We're over 20 minutes just for this one single question. Now, clearly in an exam, it shouldn't take probably 20 minutes. This is a little bit excessive. Clearly, I'm trying to explain everything as I go here. I'm trying to go into as much detail as possible as I work through the question, which clearly you don't need to do in an exam. Please don't do that. You'll get thrown out of your exam if you're doing it out loud. So yeah, definitely don't do that. But hopefully this demonstration here for part A and this demonstration here for part B has helped to illustrate how we would answer a question like this one, right, for successive oblique impacts. Okay. And there we go then. So apologies. I had this error here in the question for the coefficient of restitution. That should just be 1/2. And I'm tired. This question took over 20 minutes. I've been recording quite a few videos on the bounce here. But this is definitely the last one for today, right? But there we go then, right? So that brings us to the end then of this video here on successive oblique impacts.